We have a 5-Newton bucket of water. Now notice this time we're not telling you if it's mass or weight or a force, but the way it's being used, you gotta know some English. This is being used as an adjective. So a 5 Newton is describing the bucket, and so this is referring to its weight. So this is the weight, and also its weight because of the unit, which is a Newton. Is raised from a well by a rope. If the upward acceleration of the bucket is this, find the force exerted by the rope on the bucket. This is known as tension. First step, we're going to go ahead and identify the units, which we've done. Next, we're going to then identify the law. This is acceleration. This is second law. We're going to draw a free body diagram. Here's a bucket. Here's the rope. It has a weight going down of 5 newtons. It has a tension going up. And that's all, those are the only two forces acting on this system. So we went ahead and did with the free body diagram. Now we're going to pick a plus or minus. This is pretty important with these problems, very important. It's being raised, okay, it's going upward. Those are two hints. This is the acceleration is going upward. If I'm going to pick a positive, I'm going to pick it in the direction where the acceleration is going. So in this problem, up is going to be positive, down is going to be negative. We're doing the y-axis because this is going up and down. You'll notice we have a positive tension going up minus the weight going down. Oh, we need the mass. What do you propose we do to find the mass? They gave you the weight. How do you find the mass from the weight? Recall again that weight is equal to mass times gravity. If we divide both sides by gravity, the mass is equal to the weight divided by gravity. So I'm going to go ahead and trust that you know how to do this in a calculator. It would be the 5-Newton weight divided by 9.8 meters per second squared, and that will result in the mass. In this case, the mass is going to be 0.51 kilograms. And then A is 3 meters per second squared. This ends up being tension minus 5 newtons. If we do this multiplication, 0.51 times 3 is 1.53. Again, notice the magic here. A kilogram meter over second squared is a newton. I want to get the tension by itself, so add 5 newtons to both sides. Now, I should have asked you this at the beginning, but we have an answer, but I want you to think about the problem. Should the tension be greater or less than the weight, and why? According to Newton's second law, the greater force will be in the direction of the acceleration. So in this problem, if the acceleration is going upward and the tension is going upward, the tension must be larger than 5. Even before we started this problem, we should have thought about that and said, okay, whatever we get needs to be bigger than 5 newtons, otherwise it's a wrong answer. Okay, so we got something equal to 5, that means it wouldn't be accelerating, it'd be equilibrium, first law. If it was less than 5, then it would be second law, but it would be going downward instead. But in this problem, it was going upward. So whatever we got had to have been greater than 5 newtons because the tension must be more than the weight for this to budge upwards in the acceleration that we have. Looks the same. 5, water. Oh, there's a big difference. One's being raised, one is being lowered. Okay, so this is going upward, it's going downward. Acceleration looks the same. They want the tension again. Oh, did you catch this? I hope you did. What that is. What that is.
What that is.
Exactly. One of these is a weight, the other one's a mass. So we gotta be a little careful there. Okay, let's do this. Part B. We identified this as a mass. This is acceleration. We talked about this going downward. Okay. Let's go ahead and identify the law. Because of acceleration, these are unbalanced forces, and this is going to be second law. Weight. The weight is not 5 kilograms. That's a mass. The weight is 5 kilograms times 9.8 meters per second squared.
What that is.
So the weight is actually 49 newtons. But obviously that's not the answer to the problem because we're looking for the tension of the string. Tension is going up, acceleration is going downward, which means I'm going to make down in this problem be positive and up be negative. So that's a big reversal from the last problem, right? So if you were hoping to just use the same formula from the last problem, not quite. Okay, the change of the signs actually affects it quite a bit. All right, and furthermore, we were given different numbers as well. For instead of a weight, we were given the mass. Okay. Now let's set up Newton's second law, like we said it was. We have a downward positive 49 newtons. We have a minus tension going up. We have a mass of 5 kilograms, right? They gave it to us. That was a mass. And we have an acceleration of 3 meters per second squared. You catching the idea here? Kilogram meter per second squared. That is a Newton. Subtract 50 newtons for both sides.
What that is?
I get that tension is 34 newtons. Again, let's study this out. This answer makes sense because this is accelerating downward. So that means that the weight, the downward force of 49 newtons must be greater than the tension. Okay, so the 34 we got is less than 49. That answer makes sense for this problem. The differences between part A and part B. In part A, they gave us a weight, right? And in part B, they gave us a mass. So that was one big difference. And another one was in part A, it was going upward, it was accelerating upward, and in part B, it was accelerating downward. And that change in acceleration direction actually changed the signs. It affected what is positive and it affected what is negative. 5 kilogram bucket, here we go again. That's a mass, is lowered from a well, so it's being lowered at a constant velocity. We identified some things here. Let's talk about which law this is. If it's going at a constant velocity, that is not second law. Constant velocity means it is first law. It's got a weight going down. Based on the last problem, remember we do the mass times the gravity. It's going to give us a weight. So like in the last problem, how it was 49 newtons. This is 49 newtons as well. It has a tension going upward. It's going downward, but there is no acceleration. Okay, so don't even draw an A because there is no A. This is first law. Let's pick down to be positive and up to be negative. But look what happens. This is not equal to m times a. This is first law, so it's equal to 0. And what I have is I have 49 newtons minus tension equals 0. And if I add tension to both sides, I get that 49 newtons is equal to the tension. That makes sense because it's not accelerating. The forces must be balanced. According to Newton's third law, there's an opposite and equal reaction. And in this case, based on Newton's first law, an object in motion will stay in motion, right? Unless if it's acted upon by an external force. But there are no external forces, and these forces are balanced. They are in equilibrium. And so we have a first law effect, and therefore the weight is equal to the tension. You need to be comfortable using these words. Notice that these explanations now are involving a lot of vocabulary. I strongly suggest that you, when you meet with your group members, do your best to start using these words. Just throw them out there and start getting comfortable with them because the more you're able to talk this, the better you'll be able to understand it. Okay. For your summary, may I suggest that you reflect on the importance of labeling the signs on free body diagrams.